get started. Reminder, the first midterm is on Monday. The second one is on Wednesday. It will be from 1 to 1:50 sharp. Try to come a bit early if you can. And the first midterm, like as in the sample first midterm, will be 8 true-false with justification questions. Any questions on the midterm?
What's the Wednesday format?
Mass question, what's the Wednesday format? It's a longer question, same as sample midterm 2, exactly. Any other questions? All right, if not, we were looking at the interval scheduling problem, and in particular, we're looking at the following greedy algorithm, where, I apologize, these A sets should be S's. And so we basically sort the jobs by the finish time. And at the very first step, you put in the job with the earliest finish time. And then in the general loop condition of the jobs that you have not thrown away, pick the one with the earliest finish time. Let that be I. You put I to whatever you want to output. And then you remove all requests that conflict with I. And important point to remember also is that I conflicts with itself. So at the very least, you're removing one guy from the loop. So we have seen that the output has no conflicts, and we also argued last time that it's indeed an optimal solution. I.e., among all possible valid schedules, it schedules the maximum number of intervals. So we looked last time at the algorithm that we saw, and we analyzed it was O of n squared. Okay? And so what we're going to do today is show that you can do it in n log n, and indeed you can do it in linear time if the jobs are already given to you in sorted order. And so just to kind of give you like a sense of how you can do it, so let's say here's my input. There are 4 jobs, 1, 2, 3, 4. Now the job with the earliest finish time is 1. So the way we are currently thinking about the algorithm is we're going to put 1 in our final schedule. Then we're going to delete 2. And then we're also going to delete 3. Okay? And we've already seen if I give you one interval, if I fix one interval 1, and if I give you any other interval, how can you quickly tell whether it conflicts or not? And the simple answer is if the start time of say 2 is before the finish time of 1, they conflict. That's the only thing you need to check, again, because everything's sorted by the finish time. And so I said, given any job I, to check whether it conflicts with the first guy is just to check whether the start time is strictly before f of 1. So this is a constant time check that you need to do. And in general, and so the issue that we want to handle somehow, and now that I look at it, I realize this is not the best possible example. But imagine, if you will, that 3 actually extended a bit more, like way beyond here, right? And so the question is, okay, let me go back. So the question is, I have to remove 3 at some point of time because I put in 1, that I have to do, right? And the way we have been doing it currently, the argument is the moment we add 1, we remove 3. The question is, do you really need to do that at that point of time, right? And the point is, well, not really, right? So, I mean, so the point is, as long as I delete 3 at some later point of time, I don't have to do it now, right? Actually, yeah, this is not a good example. So the idea that the main observation is, if at some point I'm adding, say the jth interval was the guy that I added last, I really do have to throw away everything that conflicts with j. But the question is, do I do everything at that point of time or not? And the n squared time can come because the bad issue is something that conflicts with j but just kind of just goes on forever and ever, right? So let's say you have a really, really long job that conflicts with j but finishes last. Right? So then what you might have to do is, if you want to delete that last guy, you will have to kind of keep on going all the way to the end because everything's sorted by the finish time, and then delete it. And that's bad because you're skipping away stuff when you're not doing things. But the main observation here is, if this guy goes on till the end, I'll have multiple chances to throw it away, not just at that point of time. So the main observation is, throw away a job the last time you can throw it away, and not the first time you can throw it away, as we were doing currently. So in particular, if I pick an interval j, you look for the smallest index I which is bigger than, so I've thrown, let's say I've included j here, right? I look at the next guy that doesn't conflict with it, right? That's the earliest, safest thing I can put in. Everything that comes in between has to go. And you schedule that guy. And so in particular, here's kind of the final algorithm. So again, if you need to sort, you sort with n log n time, everything by their finished time. You also build an array that keeps track of the sort time. Again, this might already be given to part of the input, but if not, then you can do this. And then you initially add the very first guy to your output, because you have to. And now you keep track of what was the finish time of the last guy that you added. Okay, so initially that's the finish time of the first guy. Then you walk through the rest of the jobs in your list. And if the ith guy is after the last finish time, that is, it's not conflicting, you add that guy. And you move your finish time up front. And you keep on doing this till you are done. And the main observation here is, you throw away a conflicting job essentially towards the end instead of right at the front. And so that's it. And so that's the algorithm. Maybe talk to your friends for half a minute. Let me know if you have any questions. If not, hopefully it's clear that this algorithm is n log n, because other than sorting, everything is just linear time. All right, Evan asked for an example, so let's go through one. And I'll try to come up with an example that's interesting and not trivial. Okay. All right, so let's say this is job 1. Then this is job 2. This is job 3. And this is job 4. Right, so I have 4 jobs. The left side is the start time, the right time is the finish time. And so let's quickly go over how we would do it with the previous way, and then I kind of walk through a bit slowly how we do it with the new algorithm. So the old version Well, actually, you add I to S, which is going to be output always in both versions, right? Because they're the guy that's finishing first. In old version, you delete 2 and 4, both of them at that point of time, right? And then you add 3 to S. So this is what you would do in the old version. In the new version, and I'll just draw it through kind of arrows over here. So this is going to be my F, step 1. So I'm writing this subscript to denote which step it corresponds to over here, right? The 1 looks like an I, which is not good. Let's do A. Okay. So at the end of step A, F would be F of 1, right? Then we need to find out the largest I that doesn't conflict with A, right? So what that means is you just kind of walk through this order of increasing finish times and find the very first thing that doesn't conflict, right? So 2 conflicts, so you're not going to add 2, you're going to skip over 2, okay? So B skip over 2 as S of 2 is strictly less than F. Okay. And the next guy that you get is 3. And you're going to go ahead and add 3. So the important point to note is I have not messed with 4 yet. Okay. So the next thing is F becomes F of 3. So my F moves here. This is F, and this is part C. And now you want to look at the next guy that doesn't conflict with this. You go to 4, you see 4 conflicts, so you're not going to add it. So skip over 4 as sort of 4 times less than F. And you're done. Okay? And the reason why this gets you down from n squared to n is if you were deleting, and so think of this as a much larger thing, right? So you have, say, 1, 2, and n, which goes all the way till the end. Now, if you want to delete n, you have to skip over 3, 4, all the way up to n. So you're doing like linear amount of work to throw away one guy. And then you're coming back. And you can set up an example where at each step, you're kind of doing a lot of this back and forth. Whereas what this is saying is you essentially only do linear amount of work in each step. And at each step, you decide whether you're going to keep it in or throw it out. Okay. Tyler.
So what if, in this example, 3 and 4 were flipped? So 3 was where 4 was, 4 was where 3 is.
What do you mean flipped? In terms of
Schedule 3 right now is the same length as 1 and it's after 1.
Uh-huh.
Schedule 3 was the longest bar.
It will still be the same thing. So just to be sure, so what you are suggesting is what if 3 were like this?
No, what if it was 1, 2, then 3 at the top then?
No, top and bottom has no significance.
Oh.
It's just time on left to right. I'm just writing top to just to kind of for drawing it out. Yeah, there's no significance of top. Alex.
Did you get the intervals sorted here or we had sorted?
Right, so as I mentioned in the slide, if it's not sorted, you have to sort it by finish time. Yeah, that's why in general it's n log n because you need that much time to sort it. But if it was given to you in sorted order, everything's linear time. Because other than sorting, you're just walking through. I forgot your name, sir. Josh.
Is there any relevance to it being labeled 1 or 2 or 3? Like you step D says you skip over 4. Like how come?
Right, sorry. This is not, so for this to be 3, sorry, it has to end somewhere over here. So there is a significance in that sense that if it's number 3, that's like the 3rd in the sequence of finish time. Yeah. So
You think you skip over 4?
no, so if I say doing this, when I say skip over 4, you're already at the 4th guy.
You what?
So note that the algorithm is going through that index I. So when I say skip 4, I meant skip 4 when I is equal to 4.
The way it's drawn, does 4 come to a 1, or is there overlap?
Yes, so the question was, does 4 conflict with 1? Yes, because the start time is before the finish time. And again, I said, I'm drawing them kind of vertically just so that I'm not squishing everything together, but there is no notion of a y-axis, right? There's just time, start and end. Yeah.
If 4 didn't overlap with 1, would you pick 4 before 3, or it starts before 3?
So, right, say 4 started like over here, right, then you would, no, then you would still pick 3.
Why? Based on the end time?
Yeah.
Okay.
So there you will pick 3 instead of 4, but that's still an optimal solution.
So you would pick 3 because it ends before 4?
Everything's picked according to the finish time. Yep. Sorry, I forgot your name. Sam. Yeah, so C points to this C. Yeah. Talk to your friends. Lloyd.
What's F again?
F is a variable, so unfortunately I can't switch back and forth. It was a statement of in the algorithm, if you look, it's the finish time of the last guy that was scheduled.
Okay.
So talk to your friends. Hopefully at least one of your friends wrote down the statement of the algorithm. So look at that statement, look at that example. Let me know if any questions. If not, we'll move on. Yeah, unfortunately I can't split the screen, so you're stuck with one of these. All right, Mark.
If your 2 finish times are the same, you have to sort them by start time?
So the question was, what happens if 2 jobs have the same finish time? You can break ties arbitrarily. Our proof did not depend on how you break ties. Doesn't matter. Algorithm will always work. Evan.
Are you going to prove that this is correct?
Evan's question, are you going to prove that this is correct? No. Good thing to do it. The simplest way to prove this is to argue that the set that's output by this is exactly the same as it will be output earlier. But I'm not going to formally prove that this is correct. Josh.
This algorithm guarantees that you fit the most amount of things in, right?
So are you asking whether this is optimal? Yes. So, yes. So that's what.
I can imagine how it makes sense. If you're taking it by n time, you can probably fit the most things in, but it's not immediately clear to me that that guarantees you're fitting the most.
So what we have guaranteed is that the version of the algorithm we did on Monday is guaranteed to be optimal. And what I'm saying is what you have to prove is that the output of this is guaranteed to be exactly the same as earlier. So if you prove that, then you have guaranteed that this is optimal. So I guess that's the trick. I'll just confuse you guys and then hopefully you guys talk. All right, other questions? Alex.
Would it be correct to say that this version of the algorithm never removes the bad ones, but just skips them?
So your question is it true that the this version then removes the bad one or skip them? Well, yes and no. Yes, in the sense that, I mean, there is no step in the algorithm which says remove, right? So the version of remove in the original thing is same as skipping here. So it's more of a technicality in that sense. But Tyler.
Does this algorithm work for any schedule?
Tyler's question is yes. So as I just discussed, the algorithm that we, I'll be pedantic here. When I say schedule, you mean input, right? Because schedule is not the input, it's the output. So we argued on Monday that the previous version of this algorithm always outputs an optimal schedule for any input. And what I'm saying is the part that we didn't cover, and is a great exercise for you guys to try at home, is to prove that the output of this exactly matches the output of the previous guy for all possible inputs. Once you prove that, you're done. Any other questions? All right, so if not, let's move on. There is another version of this problem that the book talks about, which I'm not going to go in class, but again is a reading assignment, so all of section 4.1 is now reading assignment. So we'll move on. We'll still keep up with the theme of end of semester blues, but the idea is now to make the problem a bit more realistic, right? So one of the things that, so there are two things that are not satisfactory about the version of the problem, the interval scheduling problem, if I want to claim that it is kind of like the end of semester blues. One is I've assumed everything has the same weight, right? So everything is weighted the same, which is not the case. We're going to handle that assumption later on this semester. But another thing that is not true is currently the way it's stated is you have a fixed start time and a fixed finish time. Right? That is generally not the case, right? You typically have a deadline, and maybe you have an idea how long it's going to take. Right? So the picture is typically, instead of having a fixed start time and a fixed finish time, what you have is a deadline and is the duration, how long is it going to take to do the job. So the picture is more like this. You could start everything on day one, which in this case, let's say is Monday, and then you have these various tasks that you need to do, and they have the corresponding deadlines. So term paper is due Friday, exam study is due Thursday, party is due Wednesday, 3:31, and project are due Friday, and so on and so forth. Okay. And so you have more flexibility here. So in other words, previously all you could do given the intervals or jobs was choose whether to do it or not. That was your only choice, right? Here your choice is not just to choose everything or not, but when to start it. Okay? So the algorithmic task is now you figure out when to start, assuming you cannot start before Monday. So you're always given a start time. Evan.
Can you start, stop, and then start again?
So Evan's question is, can you do a job partially and then come back and redo it? No. So once you do a job, you have to finish it. It's when you look at scheduling things, and so this is called what's known as non-preemptive. You cannot preempt a job that's already going on. You have to finish it. Okay? And the version that you say is interesting, but we are not going to talk about it. And now I'll insist that you have to do all the jobs. Not only, so I'm kind of will make the problem a bit more interesting. So you can pick your start time, but now you have to finish your jobs. But now if you look at this, there is no way you can get all of them done by time, right? Because just doing the project is going to eat up all of your 5 days. So it's no longer feasible to expect, if you are doing all jobs, that you will get everything done by the deadline, which means you're going to be late for some. Right? And so what we want to do is we now allow jobs to be finished late, and you somehow want to minimize the maximum lateness, right? So you want to schedule everything so that you minimize the amount of time by which you can blow up a deadline. Okay. So I actually have removed project from here just because it was too big. And let's say I have these 4 things now. And of course, I put in 331 homework first. But, so let's say the way you schedule is you do 331 homework, then party, then study for exam, and then write your term paper. Now what you want to figure out for each job is how late were you, right? And unfortunately, you don't get credit for finishing early. So you say the lateness for doing 331 homework is 0 because you finished it by deadline. You just about managed to squeak in your party by the deadline, so it was not late again. Again, exam, you just managed to finish by the deadline, so that's not late again. Unfortunately, the term paper, you went over 2 days. So the lateness of that is 2. And the way we are going to kind of evaluate a schedule is the maximum such lateness of all jobs. Okay. So in this case, the maximum lateness of this schedule is 2. So in general, the problem now is I give you a bunch of jobs. You have deadlines and durations. You have to schedule all of them, but you want to minimize the maximum number of days by which you overshoot any deadline. Mark?
What about the project?
So that's what I said at the beginning. I'm just removing project just because I can't draw everything in there. Evan?
So we're minimizing lateness per task, not overall?
So we are minimizing lateness of all tasks, but we are aggregating everything by max. So there's another version of this thing where you could try to minimize the average lateness or the sum of the lateness. Again, a valid thing, we're just going to do max. Okay. Any other questions? All right. So what I'm going to do now is formally define this problem that we talked about. We're going to look at some examples, and then we're going to hopefully by the, let's see, we have 23 minutes. At the very least, try to come up with one greedy algorithm that we think is going to work, and we're going to start analyzing its correctness on Friday. Unfortunately, that means we have to take a break for 2 lectures and then finish it off on next week Friday because midterm comes in between. So this problem is called scheduling to minimize max lateness. And the input now are, instead of calling them intervals, I'm going to call them jobs because I can move them around, as opposed to intervals which have a fixed start time and finish time. So I have n jobs, and the ith job has 2 parameters, di and fi. Di is the deadline. Fi is, ti, which is the duration. So again, each job has a deadline and how long it will take for you to do it. And as output, what you want to do is you have to schedule each job. What that means is you have to compute its start time. And this, again, coming back to Evan's point, is a non-preemptive job. So once you fix the start time, the finish time is automatically done because you have to go ahead and complete it. Okay? So this implies I is scheduled from a start time to SI to finish time of FI, and I said this by definition is start time plus duration. Okay? So the moment you schedule something, you have to finish it off. As before, there are no overlaps allowed, so at any point of time you can only be doing one job. Okay, so one job at a time. And again, it's not that the problem of being able to do multiple jobs is not interesting, but again, something we don't have time to do. Okay? And so our goal is to minimize maximum lateness. So let's kind of formally define this too. So once I schedule job I, the lateness of job I is basically, and again remember by convention the finish time, the actual day you have to finish is just 1 before. So fi minus 1 minus deadline. Right? So if this quantity is positive, that means you were either, if it's strictly positive, it's strictly bigger than 0, it means you did not meet the deadline. And so this is the penalty that you incur. But as I said, if you finish strictly before the deadline, you're not getting any benefit. Right? So if you finish strictly before deadline, the lateness is still 0. And so for a schedule, oh, by the way, let's call this S. So now, remember the previous problem, a schedule was just which jobs you had picked, but that's no longer enough. For this problem in a schedule, you have to specify what is the start time of each interval. Okay. So for a schedule S, max lateness, which we'll denote by L of S, is just this max of this individual lateness for each time. Okay. Any questions on the problem definition? Okay, so let's do one example. So I'm going to do a simple example for n equal to 2. I have 2 jobs. Job 1 has a duration of 1, but has a deadline of say 100. So it's like really far out in the future. This, by the way, is not to scale. And the second guy has a duration of 10 and a deadline of 10. Right? So you basically have no flexibility. If you want 0 lateness for the second job, you have to schedule it right at the way you go. Okay. So again, the idea behind the greedy algorithm would be kind of similar as before, right? So we want to figure out an order in which to look at various jobs. And in this case, once you have figured out the order, you just schedule them one after the other. Right, so the moment you fix the order, in some sense, the start times are automatically determined. So one natural way to try to do this is to say ignore the deadlines and just try to schedule the jobs that will finish quicker. Right? So the first schedule, which is basically smallest duration first. In this case, the first guy is the smallest duration, so you're going to do that. And then you're going to do the second job. So you start on 1, you finish just before 2, and then you get 12 over here, right? Because it's 1 plus 1 and 2 plus 10. And now if we look at the lateness of the first guy, it's max of 0, and then finish time, which is 2 minus 1 minus deadline 1, which is 100, which is just 0 in this case. And in the second case, you have max of 0, comma, the finish time here is 12, 12 minus 1 minus deadline of the second guy, which is 10. So that's 1. So the lateness in this case for this schedule is 1. And it turns out this is not optimal, because if you look at the other schedule, which is you do 2 first, followed by 1. So in this case, it starts off 1, 11, and 12. In this case, L1 is max of 0, it finishes on finish time is 12, so 12 minus 1 minus the deadline was 100, which is 0. And L2 now is max of 0, comma, you finish on 11 minus 1 minus deadline of 10, which is 10. And so you have a lateness of 0, so the second schedule is better. In fact, if you just think about the definition, each of the lateness values is greater than or equal to 0, right? So the max lateness is always greater than or equal to 0. So if you ever get a schedule where the max lateness is 0, that automatically implies that it's an optimal schedule, because you cannot have anything smaller. Okay. So maybe talk to your friends for half a minute, I realize you guys can't see on this side anymore. Let me know if you have any questions. If not, we'll go through one example and then kind of nail down our greedy algorithm. Evan.
So your strategy for making schedule 1 was smallest duration first. Was your strategy for making schedule 2 largest duration first or first deadline first?
So Evan's question is, the strategy for schedule 1 is I did smallest duration first. In the second one, the question is it the opposite? Is it the largest duration first, or is it the earliest deadline first? Okay. We'll find out. Okay. Well, we'll find out in the sense that for this specific example, obviously both hold, but one of them would work and the other does not. Mehmet.
So for I, is that one? We're not counting the F5.
Right, so Mehmet's question is, why is that 1 minus 1, and is it because we don't finish the way you're right, our convention is when we say finish time is F5, you actually have to finish 1 time step before. Yeah. Any other questions? All right. So I think I mentioned this earlier, but let me reiterate. So just to kind of channel our thoughts in thinking about greedy algorithms for this problem, we're only going to look at a certain kind of greedy algorithms, i.e. it will fix an ordering among the jobs. And once the ordering is finished, the start times are all determined. We'll just schedule them one after the other according to the order. So you order the jobs and then schedule them one after the other. What I mean by that is, if your jobs, if you say the order is 1, 2, 3, then there is no space when 1 finishes and 2 starts, right? So there is no gap between 2 consecutive jobs. So this is what I mean, schedule them right after the other. The start time of the current thing will be exactly equal to of the finish time of the previous guy. So a natural question is, what kind of orders to consider? So we already have 3 answers, one of which we know does not work. Right, so we could do things by smallest duration first. We could do largest duration first. The other thing that was suggested was we could do earliest deadline first. And so we know that this first one definitely doesn't work because I just gave you a counterexample. And you will notice there is one thing that is common in all of these three things is you're completely ignoring one parameter. So in 1 and 2, you're only looking at duration. In the second one, and you're ignoring the deadline. In the third one, you're looking at the deadline but completely ignoring durations. Do any of you have suggestions on how you might go about combining these two, coming up with one? What would be a natural heuristic or ordering to consider things in? Alejandro.
Maybe subtract the time it takes from the duration.
Right. So Alejandro's thing is what's known as slack. So you know you have to finish it by deadline. And if you really started this job as early as you could, how much time would you have left? Right? So that's known as slack. And so let's do that. And so smallest slack. And so the slack is defined as deadline minus duration. Okay? Okay. So it turns out with one example, I'm going to rule both of these guys out. And so the only thing that will survive the two counterexamples or two examples would be the smallest. Oh, sorry. That was bad. So you'll rule out both by slack and by largest duration first. Okay. And before I go on, so our final greedy algorithm will indeed be sort everything by the deadline and then schedule them one after the other. And again, I want to point out this is kind of slightly counterintuitive. I mean, if I didn't know any better, I would have said that this had a better chance of working than this. Because one of the issues we saw with smallest duration first was we were ignoring the deadline completely. Right? And so it seems like symmetrically, if you were completely ignoring the duration, you should run into trouble. And this seemed like a good way to take both into account, but it turns out, well, you can't really ignore you can actually ignore the duration if you just pay attention to the deadline. All right, so so here's my second example. It's again n equal to 2. So again, my first job has duration 1, but it has a much tighter deadline now. So it has a deadline of 2 instead of 100. And actually, if you look at the second job, it's exactly the same as before. So let's look at the schedule that looks at the order 2 followed by 1. And note that this is also the largest duration first, and it's also the smallest slack time. Wait. I'll cheat. What I meant was largest slack. So the intuition with doing largest slack, now obviously you know it's false, but if you kind of erase your memory for the last few minutes, large slack is good because it seems to give you more time to schedule other stuff later on. So sorry about that. So you do the largest slack first, and what am I doing? No, it is right. It is smallest slack. Sorry, not a good day for me today. So if you look at smallest slack, the second job comes first because the slack is 0, and here the slack is 2. All right, so in this case, if you look at the the lateness of the first guy, it's max of 0. Then you finish at, so sorry, I should put in times here. So this is 1, 11, and 12. All right, so it's max of 0, and then you finish at 12. So 12 minus 1 minus deadline of 2, which is 9. And if you look at the second guy, it's max of 0, 11 minus 1 minus 10, which is 0. So you did pretty well with the second guy, but you really gave up a lot on the first guy. Right? And so in this case, lateness is 9. On the other hand, if you look at the second schedule, that schedules 1 first and then 2. So this is 1, 2, 12. Then L1 in this case is max of 0, 2 minus 1 minus 2, which is 0. L2 is max of 0, 12 minus 1 minus 10, which is 1. And so you get a much better lateness of 1 if you went with the earliest deadline first. And it turns out this is not a coincidence. It's not, so at the very least, of kind of the 4 heuristics, the only one that survived these 2 examples were earliest deadline first, and we're going to argue that this is indeed the best possible thing. And so what I'm going to do next is write down the pseudocode for this, do a half quick minute runtime analysis, and then we're going to look at the correctness from Friday on. Okay. So this is also known as earliest deadline first algorithm. And so you sort jobs by deadline. So what this means is once this is done, the order from 1 to, so we're going to assume that D1 is less than or equal to D2 and so on and so forth. So you start the first job at the first time that you can, and then what you do is just go in order and just schedule everything one right after the other. Okay. So for I from 1, the start time of the first guy is 1. From I from 1 to n is S of I is equal I was going to say this was the sorry, I'll have the time that the previous guy finished will be denoted by 1. So we're going to, there's nothing that happened at the 0 time, but let's finish, suppose it finished by 1. So you start the new guy at the last finished time. The finish time of the ith guy is Si plus the duration. And then you move the last finish time to this new finish time up. And then you just return the schedule that maps I to Si till Fi minus 1. Okay. So I'm not going to do this. We're going to do this quickly next time, but it's easy to see that Other than the sorting thing, you have one loop that runs n time, and every iteration is O of 1. So everything is order n. If you include sorting, it's n log n. Sorry I ran a bit over time. I'll see you guys on Friday.